Okay, so we got this. I'm just going to write down the answer in the question itself. I'm going to save a different version. Okay. So the recording we are streaming right now. So the people who are driving home and listening, that would not be safe. Okay. All right. So my computer is being extremely slow right now, so I might need to reset certain things. You're going home. You're not. But then you won't be able to ask questions. You won't be able to ask questions like, yeah, but what if I, how many points did I lose if I,
Well, I mean, I'm too scared to realize that I failed if I look at you tell me the right answers.
I see.
That's the truth of it.
Alrighty. Well, okay. You can choose your sand. Now the sand that you're going to put your head into. Not the sand that you're standing on. Okay. So bus contention, bus fight, okay, which two components can become outputs and the ports connect to each other at the same time. What do you think? Some of you must have gotten it. Through a duplexer. Yep. Yep, that is correct. All right, so good job.
So it's through like number 2 on the demultiplexer for the register.
Yep.
And then was it has to read from RAM?
Yes, so RAM has to be in read mode.
So 0.
Yep, so this is the wire, okay? This is the responsible wire, but this wire goes to many places. This D port of RAM can be an output port if RAM is selected, so RAM cell has to be a 1. RAM load has to be a 1 to specify a read operation. And then it connects to many things. But anything that's an input, like this one, is not going to be a problem. But this is an output. Okay, that's the output of a demultiplexer. So if this demultiplexer is on and it is selecting output 2, then we have a problem. So that means our register output 0 EN has to be a 1. And then this particular wire, which is our register output 0 demux, has to be a 2. So those 4 fields will basically create a bus fight.
Does the register bank have to be enabled too?
It doesn't really have to be, but since we have our register output 0 enable, that
It'll still pull the value regardless.
yeah, it's going to pull something out of the register bank. There's no way you can turn off the register bank. So the register bank is always putting something into out 0, always putting something into out 1.
Oh, okay. No, you're right.
Because when you look into the register bank, there's no buffer to turn it off.
I was going to say RE or RI enabled would turn it off, but that's just not updating it, right?
Correct. Yeah, that is just for updating the registers that you're not paying attention to the D port. You're not paying attention to the clock either when the EN is a 0. Yeah, but this multiplexer has no off switch, so they're always driving the output. But the output of the register bank directly is not causing the problem. It is through the demultiplexer that this wire is causing the issue. Okay, so all right, cool. That's the first question. So for the text version or the text portion of question 1, you just have to describe it. So in addition to specifying these fields here, so register output, was it 0? Has to be a 1. Enable has to be a 1. The demultiplexer has to be a 2. RAM load has to be a 1. RAM select has to be a 1. So these are the 4 fields that will guarantee a bus fight. The rest are not care. So depending on your version of the test, the symbol to denote don't care can be different. Can be a question mark, can be an X, can be an asterisk. So I was being a little bit tricky so that when people copying, Well, your question specifically say is an asterisk. Why are you using question mark? I don't think anyone is doing that in this class, but hey, if there's any, I will catch them. Hmm? Cannot be too sure, and it doesn't hurt honest people either. So that's the best part. All right. So question number 2 is to implement the following C control structure. All registers are assumed to store unsigned values. So that means the comparison is going to be unsigned. You have to use a JCI of some sort. Okay. So to answer this question, let me use a different editor so I can display both the question and the answer at the same time. Cool. All right. So the first one is LDI D, comma 0. I mean, I'm not even pointing. I'm not even putting point value to that one. Okay, it's really simple. So we have while begin, and okay, I'm gonna do it the same way that you have to do it because you cannot insert lines in between and stuff like that. So I'm gonna do it the same way that you do. So every while loop has a begin, and then after the begin, we do the comparison. We cannot compare to 20 as an immediate. There's no such instruction to do it. So you have to do an LDI into one of the unused registers. You can use register A or register B. It doesn't really matter which one. I'll just keep using register A as a scratch register. And then you can do a CMP. So when you perform this CMP, you can do it kind of in either direction. I would do it like this, compare D to A, and then say JCI to the inner part of the while loop. So while body, and then if that is not the case, then I jump out to while end. Okay, this is one way to do it. There's another way to do it. You can reverse the comparison. You can CMP AD, then you can do a JCI to while end. Then you have to use a to while end as well because you're looking for greater than or equal to. So that works too, but I'm just giving you one of the two possible ways to do it. Okay, so while body is going to be here. And in while body, we have to implement whatever is inside the loop, which is the conditional statement, and the increment that is outside of the conditional statement. So the first one is doing a bitwise AND with C. You have to do LDIA with 1 first, okay, and then we perform a bitwise AND. The bitwise AND has to be a little bit careful because you want to do it in this order, not CA. If you do it as a CA, that means whatever the result of the bitwise AND is going to overwrite register C, which is not the intent of the C code. So you have to make sure that you overwrite the scratch register and not register C, which is not supposed to be modified by the bitwise AND. And then after that, you do a JZI to the else branch. If you're not going to the else branch, which means the result of the bitwise AND is a 0, then you perform D plus equal to 2. You can load A with 2 and then do the add, but you can also increment D twice. So I'm just going to do increment twice, but any code that is equivalent is going to be okay. Then we have an unconditional branch to branch around the else branch. Okay, so we are going to branch to end if. And then over here we have the else branch. The else branch is just incrementing D once, so we have increment D just once here. End if is going to be right here. And then after that we have increment C. And then right after that we have an unconditional branch back to the beginning of the loop. And then after that, we have the end of the entire while loop. And that's the structure. And as I said, there are alternatives to many of these sequences of instructions. So anything that has the same result is going to be okay. In other words, I'm reading your actual code to figure out what it does. If it does the same thing, it's okay. If it reflects that you understand to a certain extent how to get this done, you get partial credit. So are there any questions about number 2? Yep.
I did one thing wrong and instead of saying and AC,
And CA?
what?
Instead of and AC, you. but that's not a compare.
No, it's wrong.
So that is kind of significant because the bitwise AND has no comparison component to it. All right. Any other questions?
Well, because and through the Z flag.
Huh? Okay. Any other questions? Nope. All right, moving on. So question number 3. Okay, question number 3 is the tedious one, depending on your student ID. So the idea is there's a loop here. So the easy way to tell there's a loop is there's a label, and then there's a branch later on to go back to that label. Now the loop is guaranteed to exit. Okay. Some people are lucky; they have the same digit, as their. So if these two digits are the same, it doesn't go through a single iteration. It would just kind of exit right away. The unfortunate person, one person actually got this combination, has a 0, 9. So it has to go through like 10 times. You have 0, 8, so you come close to the worst case. Yes.
I was not getting to this one that far, so
Okay.
the other ones.
All right. So I will still give you the correct answer to this one. I'm going to use my own ID for this purpose. So using my own ID, I'm going to say line 1, A equals to 6, B equals to 8, D equals to 8, and C equals 8, and then D equals to 6, 8, 8, 7. There we go. So line 2 doesn't do a single thing to change the values, so we can just kind of say same as before, because compare does not change the value of any of the registers. I know at least one person mistook a compare as a subtract. Ooh, that's going to be ugly because the loop will never exit in some cases, because the compare is actually changing the value of register A, but it really should not. Line 3 also does not change anything because I did not ask you guys to track or let me know what the flags are, but you still have to know what the flags are in order to determine are we branching or not. So in this case, the compare is subtracting 8 from 6. There is a carry. There's a borrow. So the JCI would actually execute and branch to label L2. So label L2 is, okay, I'll try to display the entire program, which means I might need to change the font size a little bit and maximize the screen. F11 would do it. Yep, here we go. So this is close, okay? This is close to what I need. So after line 3, I go to label L2. Label L2 is down here, and it has an increment A on line 8. So you don't have to track line 7. If you track line 7, it's not a problem. I'm not going to take any points off. So 8 is now 7. B does not change. C does not change. D does not change either. After line 8, we have an unconditional. We do execute line 9. Line 9 is an instruction, but it doesn't change the registers because it's a jump instruction. And we jump back to line 2. So line 2 does not change any registers because it's a compare. 7 is less than 8, so by the time we get to line 3, we execute line 3, and once again we branch to line 8 again. A gets incremented from 7 to 8. And then we go to line 9. Line 9 is the unconditional branch back to line 2. And then this time on line 2, the compare is going to have a 0. So the JCI is not going to branch, but we do go through line 3. It's just that it doesn't branch to L2. So then we continue onto line 4. The Z flag is set at this point, so it will branch after line 4 to line, let's see, L3 is over here, so it will branch to line 11. On line 11, we are comparing C and D. C is 8, D is 7. So the next line, which is a JSI, is not going to branch because 8 minus 7, is a non-negative value. As a result, the sign flag is going to be cleared. So the JSI on line 12 is not going to branch to L4. So on line 12, we execute the instruction, but it's not going to do the branch, so that means the next line is going to be line 13. Line 13 says the negation of C, which is basically saying C is the bitwise not of C itself. So now A equals 8, B equals 8, C is, okay, so do you guys remember the quick and easy way to do bitwise not? Yep, 255 minus that value. Okay, so 255 minus 8 is 247. Yeah. So 247, and then D doesn't change like that. And then after line 13, we have line 14. So line 14 is an AND operation, is a bitwise AND, and it changes register C itself. So what do you think is going to be the answer here? So we have 247, which is the bitwise not of 8, and then we have 7 on the other side. What do you think? This is supposed to be a, yep.
What if we assumed it was a 4-bit number?
Hmm?
What if we assumed that our ID number was only
Your ID number,
bits is that?
each digit of your ID is from 0 to 9, but once you put it into a register, it becomes an 8-bit number. So you have to perform the bitwise operations for 8-bit numbers. So you're correct, it is 0, okay? Because this is 8, so when you have, no, it's 7. Okay, you said 7. Yep, it is 7. Because all the bits in 247, they're all the bits are ones except for bit 3. Bit 3 is the only one that got turned off. 7 is bit 0, bit 1, and bit 2. So that means 247 has all of those bits on too. So if all of those bits are on in both register D and register C, then C becomes just 7. That's the result of a bitwise AND operation. Now, if you cannot eyeball this, then the best way to do it is to convert it into binary numbers first. So convert 247 into a binary number, convert 7 into a binary number, line up all the bits, perform the AND operation, and then look at the result. Yep.
Show us how you AND
Okay. So let me finish this first. Okay. So after line 14, we get to line 15. So if I really want to be nitpicking because I want to give people lower grades and whatnot, line 15 should not display registers. That should not be a symbol like this either, because that instruction technically never finishes. So it never finishes execution, so that you cannot tell me what is the value after the execution of the instruction. I'm not going to nitpick, okay? So if you guys say, everything is the same, okay, it's all cool. If you forget that, it's cool. Just tell me that line 15 is the last line that executes in this case, and it's good. Okay, so to answer your question, so 247 as a binary number is 128. Okay, so you have to go through the whole process. The other way to look at this is we knew what this came from, right? So this is 255 minus 8. 255 is 1111, 1111 as a base 2 number. 8 is 0000, 1000 as a base 2 number. So if you do this subtraction, you don't even need the long way of subtracting because there's no borrow, right? So it becomes 1111, 0111 as a base 2 number. This is 247. And then you have the other one, which is 7, which is 00000111 in base 2. And you're now performing a bitwise AND operation. Okay, like that. So the result of this bitwise operation is just going to be 1 and 0 is 0, 1 and 0 is 0, blah, blah, blah. And then 0 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 1 is 1. So that's why we have the result of the bitwise AND being 7 in this case. Okay? Any other questions about this one? Nope. Okay, cool. I think I left my keyboard in the classroom, so I'm going to go back and get it later. I don't think I dropped it here. Okay. Okay, moving on. Next question, number 4. Okay, number 4, part A is not supposed to be difficult, okay? But there is a difficult way to do it, there's an easy way to do it. So it all depends on whether you recognize the multiplier to V is by itself a power of 2.
Don't you just shift it twice?
Yep, you just adjust the exponent and you take out the sign and you're done. Oh, but you still have to show me that you know your stuff, right? So you cannot just give me the answer. You have to show me, why you did what you did.
Explain it in words.
You can do it in words. I mean, that's fine. Okay, it's not a problem. It has to be equivalent to what I'm going to show you guys here. So let me. Okay. So we look at. So you can explain it. Okay. So you can say. You probably want to convert into binary first. At least show me, that the V is represented by a double with the following bit pattern. In other words, you have to convert from base 16 back to base 2, because otherwise there's no way you can extract the bits. So in this case, it is 1100. 0100, 0111, 1110, 0010, 0111, 0110, and then a whole bunch of zeros after that. Okay, so the rest, they're not that important. So now you extract the bits. Okay, I'm just using this representation. You guys can draw a picture, draw arrows and whatnot, but using just a text editor, this is how I would do it. This is the sign flag. These are the exponent bits. And these are the fractional Mantissa bits. Okay, so once again, this is just how I would do it with a text editor, because you guys have freehand. You can draw stuff, right? So you can basically draw any way you want, as long as it conveys to me that you know how to break it down into the pieces. It's all good. Okay, so now that we have broken it into components, then you can just say that the negation or arithmetic negation means the MEANS means the new sign flag is going to be a 0. Okay. Then you say 0.25 is 2 to the power of -2, so we can adjust the exponent by decreasing 2. Okay. So your exponent as a bit pattern would now become, so E is now 100, 0100, 0101, because we are subtracting 2. Okay, so as it turns out, 2 is easy to subtract because this one here is representing the number of 2's. So since we had 1, 2, now we want to take out the 2, so just one bit becomes 0. Okay. The Mantissa doesn't change. Okay, the Mantissa or the fractional Mantissa remains unchanged. Aha, okay. Okay, so the fractional Mantissa is not supposed to change because we can do all the adjustments by the sign bit and also the exponent. So they are unchanged. So that means negative 0.25 times V can be represented as 0 as the sign flag, 100, 0100, 0101, and then the rest are the same, okay, because they are basically the same fractional part. And you convert it back into hexadecimal. The question did not ask that it has to be in hexadecimal, it just asked it has to be in a bit pattern, which means if you leave it like this, you will get full credit, because I did not ask for base 16 conversion. But if you do that one step, it becomes 4, 4, 5. That's an E. The rest are the same as the original number. So we've got a 7 and a 6, and then a whole bunch of zeros. So you missed that one part. You shifted the Mantissa on top of adjusting the exponent. Okay. All right. So are there any questions about part A? So good? Okay. Now part B is kind of asking the reverse of what you need in part A, because part B wants you to do the conversion from a floating point number, from a fractional number from a particular value, back to the internal representation. So with this one, you have to basically express, there are several ways to do it, by the way. But the bottom line is you have to know how to re-express this as a binary number, okay? You can keep multiplying this number by 2 until it is an integer, okay? If you have a calculator, you can do that. Also look up the whiteboard, the chalkboard, and find out exactly what this number should be. It's basically a multiple of 16th instead of a multiple of 8th. So if you just look at the whiteboard, the chalkboard, what do you think this is going to be? It's 70 plus something divided by 16, but what is that going to be? 0.125 is 1/8, right? 0.25 is 2/8 or 1/4. This is right in between. So that would make it what? This is right between 1/8 and 2/8. No. It's 3/16. Because 2/16 is an eighth, 4/16 is a quarter, and 3/16 is right in between. It is an eighth plus a 16th, correct? Yep. But using the numbers on the chalkboard, you can actually guesstimate, what multiple of 16th it is. If you have a calculator, you can also keep multiplying this number until it becomes an even number. Then you can just convert the even number to binary, but keep in mind how many times you have to shift it. So did you guys have a scientific calculator or just any calculator? Okay, so I can show you that technique too. I may or may not have a calculator here. I do not have a calculator here, but that's okay. I can actually do it in a slightly more obscure way.
So it's basically 0.125 plus 0.0625 or 65 or something like that?
Yeah, so basically you look at this number.
I did like it was base power negative 2 to the negative third and then 2 to the negative fourth, I think.
Oh.
Something like that.
Okay, so let me just kind of finish this one. So it's 64 plus 4 plus 1/8 plus 1/16, right? So now you have 16. This is 2 to the power of 8, 6, sorry, plus 2 to the power of 2, plus 2 to the power of 1, plus 2 to the power of 0, plus 2 to the power of negative 3, plus 2 to the power of 2 to the power of negative 4. Is that okay? So 2 to the power of whatever is 1 followed by that many zeros in binary. So this is 1, 0, 0, 0, 1, 2, 3 in base 2, plus the second one is 2 to the power of 2, which is 1, 0, 0 in base 2. The next one is 2 to the power of
It's 1, 0 to the power of 2.
oh, I think I got, okay. I made a mistake here, sorry. There's no 2 to the power of 0. So that one should be gone, okay. So this is 2 to the power of 1, which is 1, 0 in base 2. Okay, so the fractional part is basically how many places to the right-hand side of the decimal point. So if it is 2 to the power of negative 3, then it is 3 places to the right-hand side, which means you have 2 zeros. So this is 0, 0, 1 in base 2. And then the next one is 0.0001 in base 2. So now that I have everything in base 2 and lined up, we can just do the quick addition, which means I get, so equals to 1000,110.0001 in base 2. So is that conversion okay? Oh, right, I forgot that one. Sorry, there you go. Okay. So is that okay so far? This is actually from the previous test. In the previous test, you know how to do this already. It's just that the values are a little bit more spread out in this case. Okay, so now that you know this is the value that we want to represent, then it's just a matter of shifting. In other words, you want to shift this binary point all the way to here. So every time you shift the binary point to the left-hand side, what do you do to the exponent of 2? You have to increase it by 1. And how many times do we have to shift it here? 6 times, right? So it basically you can jump to this step. You don't have to show me all the individual steps. So it's 1.00011100011 times 2 to the power of 6. Because originally there's an implicit times 2 to the power of 0. So you just increase that implicit 0 all the way to 6. So the next thing we need to do is now to separate the sign flag. The sign bit is a 0 because the value is non-zero, non-negative. The exponent is going to be 6 plus 1023 because we have to remember there's a bias of 1023. So that means this is actually 1029. And as a binary number, it is 1024 plus 5, which means this is 1 followed by 10. Well, we'll do it the long way. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus a 4, which is 100 plus 1. So that is basically 1. Okay, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Backspace 3 times. There we go. The mantissa is the fractional part. Okay, so you have to remember the 1 point is not represented anywhere as the fractional part. So the mantissa that we want to put into the double precision floating point number is 00011 and then followed by all zeros after that. So then you stitch everything together. The sign is a 0. The exponent is 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1. And then the mantissa, or the fractional part of the mantissa, is 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, and then a whole bunch of zeros after that. And I think this one I did specifically ask for a hexadecimal representation. So now you have to group these by 4. And on a piece of paper, you can do it kind of just by drawing some vertical lines to help you break it into groups of 4. But in an editor, I would do this instead. Okay. So now it is a 4, 0, and 4, 0, 5, 1, 8, C, and then a whole bunch of zeros. So in this case, I have 6 non-zero digits out of 16, so I will need 10 zeros after this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be the answer for this particular value. Is that okay? So I guess the most difficult part is really the first part, which is actually common to the first exam. The second part is really just testing. Do you know how the exponent works? There's a bias of 1023. Do you know it is an 11-bit thing? And do you know that the mantissa is only the fraction part? The 1 point is not included. So are we okay so far with question number 4? Okay. So moving on to question number 5, last question. Okay, the last question is basically testing, do you know how to reverse assembly code back into C? So you basically have to analyze the program in a particular way. You have to analyze it in a structured way. Okay, so we'll start with, it's a little bit harder for me to kind of do it on the projector. I can kind of use the mouse pointer to kind of help direct your attention of where we should be looking at. All right. So for every label, okay, so the key is to look at the label and look at the branch to those labels, okay? So unless I'm really tricky, give you some extra labels that have no go-tos or jumps corresponding to those labels, every single label has a purpose, okay? So you look at label 1 and go like, well, where's the jump to label 1? It's all the way down here. Okay? Every time you have a jump back to an earlier label, what kind of control structure do you know you have? Has to be some kind of a loop. So we only got two kinds of loops. We have a while loop and a do while loop. Those are the only two loops that we talk about in this class. So when you look at the module, a do while loop has a conditional branch back to the earlier label. A while loop has a unconditional branch back to the beginning. So because the branch that I have highlighted here is unconditional, that pretty much tells you that it is a while loop. Okay? So from just this part, I can now say that we have some kind of a while loop with some kind of a condition. Okay? We can at least conclude this much. Okay? Yep.
Could you say that one more time? Since the branch is unconditional, it's a while and not a do.
It is all in the module. There's one particular module that talks about how to compile a C control structure into assembly code. We flatten the code of a while loop. We look for the reason to exit the loop, and then we perform the body of the loop. At the end of the body of the loop, we have an unconditional go to back to the label, which marks the beginning of the entire thing. Okay, that's in the module itself. So the unconditional branch is a jump I instruction, and it's jumping back to L1. So that means this part here, this entire thing is a loop. Now, what is inside the loop? Well, that's kind of a second question. Is that okay? All right. Okay, so the second thing you have to analyze with a loop is how are we getting out of the loop? Okay, I know in a C construct you're asking how are we staying in the loop, but in assembly language programming we do not have the construct of a loop itself, so we can only answer the question of how are we getting out of the loop. So the label that is corresponding to getting out of the loop is L3. So now you're looking for how do we get to L3? There's only one conditional branch of L3, which is the JZI instruction. So now your question is, how do we get to L3 through the JZI instruction? How do we even get here? So that's your question. You have to kind of work your way back up a little bit now. Okay? So in order for this branch to be successful, there are several things that you have to do first. First of all, if you just back up one step, okay, how can the compare instruction, how can compare BC guarantee that the JCI instruction will go to L3? That's the first question. What do you think? So B and C have to be the same. Okay? So B and C have to be the same, but that's my exit condition, not stay in loop condition. So to stay in loop, we want them to be different. Okay? So I'm going to go back to code here. I'm just going to add some more information here. Okay? I'm just saying that B does not equal to C seems to be kind of important to stay in the loop, because when B and C are the same, we're getting out. Is that making any sense? Okay. But then we go like, but even to get to this part, we have to make sure that the previous branch instruction is not branching, because if I'm branching to L2, I'm not getting out of the loop. Is that right? So now we have to say, how can we make sure the JCI instruction is not branching? In other words, how do we make sure that after comparing A to B, the carry flag is cleared? That becomes the second question. So what do you think? A minus B does not have a carry. What does that mean?
So B has to be
A cannot be less than B,
yes.
unsigned, right? So that means here, I'm going to say A is greater than or equal to B to stay in the loop. Oh, sorry. A is less than B to stay in the loop. Because if A is less than B, I go to L2, which is the body of the loop already. Is that okay? So A is less than B is the immediate reason to stay in the loop. Don't even consider getting out of the loop. If A is not less than B, I'm not going to L2. Then we actually compare B and C and say, okay, how is B comparing to C? If they are the same, then we get out. So B equals to C is an exit condition, but only if A is not less than B. If A is less than B, we stay in the loop right away. So I think I have just hinted what logical operator you need to connect these two. In other words, what kind of operator do we need to put here? Nope. Because if it's an AND, it means both conditions have to be true to stay in the loop. But this is basically saying if A is less than B, let's stay in the loop right away. I don't even bother to check B and C. So it's an OR. It's only when A is less than B is false, then I will go, okay, fine, we'll check B and C. So it's a logical OR out here. If you put in an AND, you'll get some points deducted, but not a whole lot. Because just recognizing that there's a logical operator to connect the two comparison is worth points already. Now, do you use the right logical operator? That's extra. That's partial of a part of that chunk. Yep. So are we still doing okay so far with this? Yep. If A is greater than or equal to B, then the carry flag is going to be cleared. Then we get to here and we'll compare. We'll compare B and C in that case. If they're not equal to, then we stay in the loop. So that means if B does not equal to B, if B does not equal to C, we stay in the loop. That's my second reason to stay in the loop. Because falling through is still stay in the loop. The only way to get out of the loop is to go to L3. Is that answering your question or? Okay. Okay, so now what do we do inside the loop? Now that we know the loop has what kind of condition it is, where's the beginning, where's the end of the loop. So what we are really asking is we are now looking at this chunk of code and say, what is that code? Now, the nice thing about structured programming is when you're trying to decipher this chunk of code, it has nothing to do with the chunk that we have already deciphered. This is all stuff that is happening inside the loop. So we are now looking at just inside the loop, inside the open and close curly braces, and go, okay, what goes in here? So what do you think is going in here? We have a comparison, okay? So how do we know this is an if statement and not another embedded or nested while loop? You look at the branching, right? So out of the highlighted portion, are there any branching back to an earlier label? Branching to L4 is in the future. Branching to L5 is in the future. Branching to L6 is also in the future. There's no branching back, so there's no loop. There's only one control structure that we talk about in this class that is not a loop, and it's a conditional statement. Okay? So now I can say, okay, we know at least this much. The question is, do we have an else? What do you think? We do have an else because there's a branch around something. That tells you that we have a then and an else branch. Now, which one is which one? You can switch. Okay, so if you reverse or invert the condition and reverse the then versus the else branch, it's okay. You get full credit. But you do have to identify that it is a dual branch type of conditional statement, not a single branch conditional statement. So we do know that there's an else. Okay. So now the question is, okay, how am I deciding to go to the then branch versus the else branch? Well, we have a compare and a conditional branch. That is how we decide whether to go for the else versus the then branch. We know it has something to do with A is less than B, okay, or the negation of that. So now it is really just up to you to decide, do we want to consider L4 as the then branch, or do we want to consider L5 as the then branch? It's kind of up to you, because I don't want to enforce a particular standard. But my usual way is L4 is the then branch, so I'm going to do it that way. So now the question is, how do we get to the then branch when A is less than B? So when when A is less than B, we go to the then branch. When A is not less than B, we go to the else branch. What do we do in the then branch? We increment A, which means A plus plus. Okay. And then we do a JMPI to L6. Do not do this, please. Okay. If you give me something like this, I will take points off, because the questions specifically say do not use go to, break, or continue. So, and it is not necessary either, because of the nature of a conditional statement in C, because of the structured programming method, it does not need a branch around the else branch. Okay, so now we get to the else branch, which starts at label L5. It's a CPR instruction, which is a copy register, B equals C. That's it. That's the entire program. I think most people got a good portion of it. The most tricky part is the or versus the and. I think that's the trickiest part. Yep.
I don't think B has to not be equal to C. I think it could exit even if B is not equal to C.
Okay. So you're saying that B does not have to be different from C to get out of the loop. Oh, excuse me, take it back. B does not have to be equal to C to get out of the loop. Is that what you're saying?
Yeah.
Okay. So, and tell me how that can happen. Give me a scenario.
So at the L1 or yeah, and then when you'll compare A and B, and
Yes.
they don't throw carry, and then you compare B and C,
Yeah.
once they're not equal to each
It,
other, and then you would continue to L2, right?
yes.
And then you would continue to CMP AB, and
Yeah.
it didn't fire both, so it's not going to fire again. And then
Say that one more time. What did you say?
I said it didn't fire the first time, so it's not going to fire the second time.
That is correct. So we go to L5.
So we go to L5 and you
Then it copies C to B, which guarantees that they will be the same, doesn't it?
JCI.
In the JMPI, after the CPR instruction, we fall through to the jump I instruction,
Copies B to
which,
C. Oh yeah, so it does guarantee they will be the same. Yeah.
well, it guarantees that it will exit the loop. But not only that, but it also guarantees that if A is not less than B, I will make B and C the same.
Yeah. So you don't need to include B is not equal to C in the while loop because the else branch takes care of
But that's not what the question is asking. The question is asking you to convert the code to the equivalent C code.
yeah,
That's what was kind of
the
confusing
equivalent
because
C code doesn't
I
do
was
that.
looking
It
at it, it
really
didn't really make
fires.
sense. And then when you actually said, even though it doesn't make sense, do it regardless. And I was like,
Yeah.
oh.
Yep. Yep. Because the question is not asking you to track the execution of the code. It's asking you, do we know how to reverse it back to the C code?
So we're just following the instructions.
Yep. Yep. Exactly.
So what exactly says that to put the B is not equal to C?
Say that one more time.
So what exactly from the assembly code says that you need to put B is not equal to C?
It's right here. Compare B to C, JZI to L3.
Yeah, but if you didn't have that step in L5, it could just exit the while loop.
If I did not have what again? If I do not have this?
Yeah.
If I don't have this, then it will not exit at all. Because if I don't have this and B and C are different to begin with, and A is not less than B to begin with,
Well, your loop could assume like B is a number and then be incrementing B and then it could come.
there's nowhere that is incrementing B. Where are you getting the incrementing B part?
Saying that if the code were different, it could increment B and exit the loop without using a compare, and in that case, the B is not equal.
But that is not that's not the instruction that is given to you. You have to work with the actual instruction that is given to you.
Don't imply that I have to have B is not equal to C.
Say that one more time. The instruction given to you does not imply
That B is not equal to C.
that B does not equal to C.
Necessitate that B is not equal to C. I mean, in the while loop, it's not necessary.
I'm not getting your statement.
Because this is a compare.
That is not a compare.
I mean, no, since it's a copy register, since this equals this,
Yes.
and when you exit, this will always be true. But this doesn't mean that this has to be in the while loop, because it could go all the way through without this happening if this were different.
What is your answer then?
What?
What?
It's this
What are you proposing that is equivalent to this?
everything except that.
Then it's not going to exit.
Yeah.
If you don't check for that, I can make B and C the same, but if you're not checking whether they're different or not, it's not going to exit. The behavior of this code, of your code, is not going to be the same as the assembly code, so they're not. It's not going to get full credit.
Yeah, I understand.
Yep.
It was a little bit.
Hmm?
Kind of made me think for a second too.
Yep, because your job is just to reverse the code back to the structure C code and not really to question, oh, what does it do? What is the purpose of this code? The only purpose is to use it in the question and see whether you can recognize the structure of the code. All right, so we got all 5 questions. Are there any questions about these 5? Nope. Okay. So just keep in mind, of how I break down the letter grade, okay, because it's not really the same as the rest of your other classes. And then number 2 is, I do give partial credit, but the partial credit is based on, is your answer demonstrating that you understand a particular concept and know how to apply that? Okay, so that is how I assign partial credit. It's like, well, it's not entirely correct, but I can see that you demonstrate that you understand this, or how to apply that. Okay, that is how I would give you a partial credit. All right, cool. All right. I'll see you guys on Thursday.